In this lesson, we're going to talk about the greenhouse effect and greenhouse gases. So when we look at the Earth, or let's talk about a greenhouse to start off. You can see the little image here of the greenhouse in the middle. When the sun shines down, the greenhouse lets the sunlight come through the windows. The windows are either made out of glass or out of plastic. It heats up what we have inside, the vegetation, the ground. But lots of that heat doesn't manage to leave the greenhouse, and so it's a lot warmer inside the greenhouse. Some of you may have experienced this when you park a car on a cold day outside, say in a shopping mall parking lot. When you come back to the car, it's nice and warm inside. That's also the greenhouse effect. The sunlight's coming through the windows of the car, heating up the seats and the inside of the car. The heat cannot escape out. It's not a perfect analogy to what happens on the planet Earth, but it's good enough. And so what happens on the Earth is, instead of windows, we have an atmosphere. And the atmosphere has gases in them. Some of these gases, not all of them, some of them are called greenhouse gases, and they have a similar role to the windows of the greenhouse. They let the sunlight coming in. The sunlight heats the surface, heats the oceans. The heat then goes out, but not all of that heat can actually leave the planet, and a lot of that gets trapped in by these greenhouse gases. Now, this happens naturally on Earth, and mainly because of water vapor, H2O. Water vapor evaporates from the ocean. Water vapor is only about 1% of all the air in the room at the moment, but this causes the Earth to warm up. You can think of it as putting blankets on the Earth, warming up the Earth, and allows us actually to live here on planet Earth. And we'll talk about this later in the course, but I'll already tell you that without the atmosphere, the temperature wouldn't be 15 degrees here, it would be minus 18, and the oceans would be solid ice, and we wouldn't be living here today. So it's good we have a greenhouse, what we call a natural greenhouse, and this is mainly due to water vapor in the atmosphere. The problem is today we're adding a lot more greenhouse gases, and the greenhouse gases are carbon dioxide, nitrous oxide, and other gases. And what makes them greenhouse gases is their chemical structure. In fact, the greenhouse gas has to be an electrically asymmetric molecule. If it's symmetrical, it doesn't absorb heat. And most of the air in the room around you today is oxygen and nitrogen, which is symmetrical. And so oxygen and nitrogen are not greenhouse gases. They do not warm up the planet. Only a small amount of them, like water vapor and carbon dioxide, nitrous oxide, and methane, these are asymmetrical molecules. So when the heat or the energy hits these molecules, it causes them to vibrate, to rotate, and we lose some of that energy in the system instead of it leaving and cooling the planet. And what actually happens is that when we have, say, a ray of sunlight or some heat which hits the molecule, here we can see an example of CO2. The white or gray atom is the carbon, and we have two oxygens. The energy which hits the molecule, some of this is absorbed by the molecule and will cause it to vibrate, and means that less of it keeps on going out to space. And so overall, when we have greenhouse gases, they tend to trap in more and more energy. They can vibrate in many ways. Here we can again see CO2, which on the right-hand side is vibrating in different ways. The different ways are determined by the actual amount of energy that they absorb, but in the long term, less energy is leaving the Earth and going out to space. And again, we can think of it as we're putting more and more blankets on the planet Earth as we increase the amount of greenhouse gases. So today we're adding a lot more greenhouse gases to the atmosphere. Most people talk mainly about carbon dioxide, and this is really the biggest problem, because it's simply the most of the greenhouse gases that we're putting into the atmosphere are carbon dioxide. But we also have methane, CFCs, chlorofluorocarbons, ozone, and nitrous oxide. All of these are increasing quite dramatically in the atmosphere, and we believe that this is because of man-made activity on the planet. So here we can see the increase just over the last decades of the four main greenhouse gases that we're talking about, and we'll talk about each one separately in a few minutes. But we have carbon dioxide on the top left. We have the chlorofluorocarbons on the top right. We have nitrous oxide and methane. And if you look carefully, the color of the graphs shown at the bottom also matches the image on the right-hand side. So for carbon dioxide, the main source of carbon dioxide is really the burning of fossil fuel. Fossil fuels are fuels which came from fossils, which means they were once plants or animals filled with carbon. When you take that and burn it with oxygen in the atmosphere, we get carbon dioxide. So all of the fuels, the fossil fuels we're using to generate our electricity, the gasoline in our cars, in our buses, all of these are using fossil fuels today, or most of them, resulting in increases in carbon dioxide in the atmosphere. When we look at the chlorofluorocarbons, the top right here, today we've shifted slightly away from the CFCs to HCFCs because of the ozone layer, which we're not going to talk about in this course. But basically from the cooling of our houses, of our cars, our refrigeration, we use these gases, and we use them because they absorb heat very well to cool the room and to cool our homes and our refrigerators. But when we throw away these air conditioners and fridges, or just the production of them, and these gases leak into the atmosphere, they trap the heat of the earth and don't let that heat leave and go out to space. When we look at the nitrous oxide, the bottom left, this is mainly due to fertilizers for agriculture. We have nearly 8 billion, nearly 9 billion people on the planet. We have to feed them all. And so we have agriculture which uses lots of fertilizers which are very rich in nitrogen. And this again reacts with oxygen in the soils, and we have increasing concentrations of nitrous oxide. And finally, methane, which has a kind of a funny shape, the increase. Although it kind of slowed down in the 1990s, the increase, but in the last few years we've seen a dramatic increase in the concentration and an acceleration in methane. And this comes also mainly from agriculture, from beef, but also growing of rice. And we'll talk about each one of these individually in the next few minutes. So who's to blame for all of these increases? Which sector in the economy really is to blame for it? So here we can see that it's an extremely complicated problem, but 50% of the problem is really the consumption of fossil fuels. Again, to produce our electricity in our homes, in our industries and buildings, heating, cooling, and in our cars, in our transportation, this results in this is the main problem really. 50% of the problem is the use of fossil fuels. The chemical industry gives another maybe 20%, and this is mainly from these chlorofluorocarbons, the halocarbons, which are used in the industry for cooling, for refrigeration, but there are also other uses. I should point out the amount of these gases is tiny in the atmosphere, but because they're so efficient at cooling our rooms and our cars, they're extremely efficient at absorbing heat. So even a small change in these chlorofluorocarbons results in a big impact on global warming. Then we have agriculture. Again, we have to feed the planet, about 15% of the problem. And here there are many areas, both from fertilizers, the growing of beef, rice farming, waste disposals after all of these produce greenhouse gases which impact global warming. And then finally, we have deforestation or land use changes on the planet, which is about 15% of the problem. We know that when we have vegetation, we have photosynthesis, which takes up carbon dioxide and stores that carbon dioxide in the trees, in the leaves, in the roots. You can think of it kind of like a bank of carbon. But when we chop down the forests or we build cities and we get rid of the vegetation, it's the same as putting extra carbon dioxide into the atmosphere. So changing the surface of the earth, changing the biosphere, is also having a big impact on the concentration of greenhouse gases in the atmosphere. So let's talk about each one of these greenhouse gases, the main four, just for a few minutes. The first one, and the main one again, is carbon dioxide. And we can see here the timeline from the 1700s, from the Industrial Revolution until today, of the emissions of carbon dioxide into the atmosphere due to the use of fossil fuels. And we can see that initially, in the 1800s, we had the steam engine, and we were using mainly coal. Coal was the main source of the fossil fuels, easy to dig out of the ground, to simply burn it. Then in the beginning of the 20th century, we started to use more oil and petroleum. And later on, around 1950s, we started to develop a natural gas, which is increasing quite dramatically now. And there are a few other sources, small ones, just interesting sources. If you look at the bottom right, cement. When we produce cement to build our cities today, cement is basically produced by taking limestone rock and putting them in furnaces to get lime. But what are limestone rocks? They're also fossils. They're basically the shells of animals which died in the oceans and built up this limestone. which used the carbon dioxide in the atmosphere then. And now if we take this and put it in an oven, we basically release that carbon dioxide back into the atmosphere. So it's not a major source, but it's becoming important because of all the building going on around the world. But notice what's happened just in the last few years. Coal again has become the main source. It was only the main source until about the 1950s, and it's taken over again. It's become more important than others. The reason for this is we can see over here. Here we can see the main countries which are contributing to the emissions of greenhouse gas. And if we look what's happened in China since 2000, we know the development which has taken off in China. And China are building, the economy has been growing so rapidly, they're building coal-fired power plants nearly every month or so. They need all this energy, and they're using mainly coal. And so coal has become now the main source of energy, basically because of the changes we're seeing in China. But I need to point out that even though on an annual basis today, China is the biggest emitter of carbon dioxide, when we're looking at the effects on the climate, we have to look at the long-term emissions, because carbon dioxide, every molecule has a very long lifetime, maybe 100 years. And so what's important on this plot is actually the area underneath these plots. And then when we look at the area under the plot, United States and the EU are still the biggest contributors to carbon dioxide in the atmosphere. When we look at the energy consumption over time, from the 1960s to the present, we can see here the top three curves are again the energy we generate from oil, coal, natural gas, and way down at the bottom we can see the renewable energies. So we're very far away from really replacing these fossil fuels, but to solve the climate crisis, that's what we actually need to do. But we're so heavily reliable on fossil fuels, and this is going to just increase in the future as the population of the planet grows, and we're going to have more needs for energy. So we have a big problem that we have to deal with, and it's a huge challenge facing us, how we can move away from fossil fuels and still drive our economies and move more to renewable energies. And we'll talk about this during the course, and also near the end of the course, we'll talk about solutions for the climate crisis, which take into account these issues. Now, if we focus on the measurements of carbon dioxide, we really only started about 1957. There was a huge global campaign called the International Geophysical Year, where the United Nations asked all different research institutes around the world to start measuring what's happening on the planet. So in Hawaii, on a mountaintop in Hawaii, a scientist, Keeling, started to measure. And this curve you see here is called the Keeling curve from Scripps University. And thankfully, they started to measure in the 1950s because of this long-term measurements do we actually have data showing that carbon dioxide is rapidly increasing in concentrations in the atmosphere. The small insert you can see here shows actually the annual cycle of carbon dioxide in this plot. You can see the ups and downs every year. And this is actually because of the breathing of the planet. When we have growth in the spring of plants, we have new leaves, new trees growing. This takes up carbon dioxide from the atmosphere, and we see a decrease in carbon dioxide measured in the northern hemisphere. This is a plot representing the northern hemisphere. And at the end of the summer, when we have the decay of organic matter, the carbon dioxide is released back into the atmosphere. So we have this annual cycle every year, which will be exactly the opposite shape in the southern hemisphere because the seasons are different. But on top of that, we have this black line, which you can see, which keeps on going up and up and up. And if in 1957, when they started, the concentrations were below 320 ppm, which is parts per million. If we have 1 million molecules, 320 were carbon dioxide. Today, in 60 years, we've added another 100, so we're close to 420 ppm. So this is very significant, and we'll also show you in the next class how significant this is when we look hundreds of thousands of years back in time. As I mentioned, when we change the vegetation on the planet, we also change the amount of carbon dioxide in the atmosphere. And this is a big problem with tropical deforestation today. Brazil is one of the main culprits, but we also see in Indonesia and in the Congo, many of the developing countries in the tropics are cutting down the forests, and they're not 100% to blame themselves. We also have part of the blame, because a lot of the reason they're chopping down the forest is to grow food and to grow beef and hamburgers for us in the West. But when you chop down the forests, and you can see the satellite images in the bottom from 1975 to 2021, you can see that there was a road actually built into the jungles in the 1970s. And as soon as you have access into the forests, people go there and they can start to clear the forest to make subsistence farming. And even the government encouraged them. It kind of got the people some way to have a livelihood and to support their families in the region. And the clear areas you see on the side of these rows are areas which have been deforested, where the forests have been chopped down, like in the picture on the top. And not only do they chop them down, but they even burn them. And when you burn them, immediately the carbon goes back into the atmosphere as carbon dioxide. And so this trend of deforestation is basically also contributing to the increase in carbon dioxide in the atmosphere. And here we can see the effect of the deforestation or changing vegetation over time with the blue curve at the bottom, compared with the changes in carbon dioxide from the burning of fossil fuels. And until about the 1950s or so, these were kind of the same order of magnitude. Since then, burning of fossil fuel for our economies and our cities has taken off, and we can see it's much higher. But still today, about 20% of the problem of carbon dioxide is because of tropical deforestation. So we need to deal with that as well. Let's move to the next greenhouse gas, methane. Well, here we see a fairly good correlation between the number of people living on planet Earth and the amount of methane in the atmosphere. Here there's a direct link between the number of people we need to feed, because methane is coming mainly from the agricultural sector, but also others. But we see as we have more people on the planet, we also have more methane in the atmosphere. And if we look at the different sources of methane, first of all, there are natural sources, and this is one of the problems with the whole debate in climate change, that both carbon dioxide, methane, and the others, there are natural sources, and we don't really have a way to say that this molecule we detect in the atmosphere is natural, or it came from a factory or from agriculture. And so there are natural sources also of methane, and we can see them here from mainly from regions where we don't have any oxidation. For example, wetlands or swamps and bogs are areas where plants are growing in the water, and this gives off methane. Termites also are a source, and there's some from the oceans and freshwater bodies. But the majority today are man-made anthropogenic sources of methane, where we're talking about livestock. And this is livestock that chew the cud. So not all livestock that chew the cud. And unlike what most people think, it's actually methane coming out of their mouth, most of it, while they're burping. Rice paddies and the growing of rice in water actually causes emissions of methane from the rice paddies. Landfills, as I mentioned, biomass burning, also the gas production, natural gas, and leaking of pipes, which are transporting the oil and gas around the world. All of these contribute to methane increases in the atmosphere. And here we can see how the production of rice has increased from the 1960s to the present, as well as the cattle production, which a lot of this is in the tropical areas. And again, this production is increasing because there's a demand. The population wants to eat, and there's more people we have to feed. The more people on the planet, the more food we need, and this is resulting in increases in methane emissions and concentrations in the atmosphere. The next gas of importance is nitrous oxide, N2O. This comes basically from one source, and that's fertilizers that we use for agriculture. In order to feed the planet, and this will be true in the future too, we have to do intensive agriculture because we're running out of area, and we need to feed a lot of people. And so fertilizers help us grow food quicker and better, but they also result in the emissions of nitrous oxide, because fertilizers are very rich in nitrogen. And again, nitrogen and oxygen give us these molecules. And we can see the increases here over the last decades. And the last greenhouse gas of importance are the chlorofluorocarbons. These are made up always of these three atoms: chlorine, the C, fluorine, the F, and carbon, the second C. And there are different combinations of these atoms which give us different types of CFC11, CFC12, and now they also have a new type we call HCFC, which adds a hydrogen atom. The change was because of the effect on the ozone layer, which I'm not going to go into, but so the CFC 11 and 12 have actually been removed from production, and we can see the decrease over time. They're starting to decrease in the atmosphere, although they have very long lifetimes, so it'll take a long time to clean them out of the atmosphere, while the HCFCs are now increasing quite dramatically, and while they may be better for the ozone layer, they still trap in the heat of the Earth and cause warming.